Welcome to Transfer Phenomena in Bioprocess Engineering NPTEL course. So, this is lecture 4. We discussed in last class dimensional analysis and dimension numbers, few in the bioprocess engineering, how we have to solve using Buckingham theorem. But the continuation of the previous class, today we will discuss about the natural convection heat transfer in the outside the vertical plane. So, it's what is the natural convection? Forced convection. The forced convection, until if you give some force, then due to force the convection taking place, that is called a forced convection. But natural convection is a gravitational force. So, here in the due to gravitational, this one how the natural convection occurs, because two type of convection is there. One is the forced convection and one is a forced convection. Okay, other one is the natural convection. Last class we discussed a forced convection, but this class we discuss about the natural convection. So, you assume the like vertical plate immersed in the still air. So, initially the air and plates are same temperature, the temperature is same, but once it start to heat, the temperature changes, okay, Ts here. So, here the buoyancy force, mainly what we see distance here, discussed here buoyancy force. The buoyancy force only depends on the these variable. It is called beta, then the g, rho, then delta t. Okay, these are the buoyancy force variable. Before solve, and we need basic fundamental, what are the variables we have to use here. So, first starts with the h. H is the heat transfer coefficient. Heat transfer coefficient, we write always the units watt per meter square Kelvin. The length is the meter. So, the dimension is L, because we can write M, L, then T, T. These are basic dimension. So, whenever mass involves, there is a kg mass here. The L is the length is always we write the meter. The T we write the time. Then another T is the temperature here. So, the first one is for watt per meter square Kelvin. So, watt we can again replace, okay, joule per second. Then meter square Kelvin, just I will show only one. Okay, the joule, what we have to do, we always write a force into distance, Ws here, F into S. F we can write MA into S distance by meter square Kelvin. The M stands here, mass. Okay, that we always write M, the here acceleration L by T square, then again here one more L is there, the distance S, then down is M square Kelvin. After that this one, so the length we always write a L square, then we will write here meter square, we will write a L square. So, we will get cancel, then finally we get M T power T. So, one is the mass, then the T is the time, then the temperature. So, here the W first what we have to replace, W equal to the force in the distance. The force we can write M into A. M is the kg, then A is the acceleration, meter per second square. So, then other one is for the distance here, distance also we can write L. So, finally, this all if you solve it, then we get in terms of M power T power 3T, the length is a meter, then delta T the temperature difference, because here the temperature difference main here. So, then we have to discuss about the K, the unit is Kelvin, the dimension we always write a T, whenever Kelvin we write a T. So, then mu is the viscosity is the kg per meter second, the unit is here, the kg we write M, then L is a meter, then T is a second. The density kg per meter cube, so we can write M by L cube. Same way for specific heat capacity Cp, joule per kg Kelvin, that we can write L square T square, again here joule, same way joule work equal to force into distance here. So, then we have to write like way. Then the K stands thermal conductivity, that watt per meter Kelvin. Then what we can write, what is here joule per second, then another is meter per Kelvin. So, you have to again convert all in terms of the fundamental dimension units, then finally we can arrive the L square T square T. Same way watt per meter case also we can arrive here. The beta volume expansion thermal coefficient we write 1 by K, then the 1 by T here. G is a gravitational this one. So gravitational we write m by s square. So L by T square, L by T square. So these are the dimension, fundamental dimension, these are units. So first you have to form like this. Then Buckingham theorem, what they are saying, the total number of variable. So how many variable here is a 1, 2, 3, 4, 5, 6 up to 9 variable. So we have 9 variable, here, but the fundamental, what is the fundamental dimension unit is a u equal to 4. What is the u equal to 4? Mass m, we write mass m, length is L, then the time is the T, then temperature is the T. So that is a small t, the capital T. So totally the fundamental dimension unit is a 4, but the variable is 9. So if you want how many number of dimensionless numbers, you can always write the P is a function of variable then fundamental dimension units. So here what is the variable, how many variable? 9 variable, the fundamental units here 4. So we have to get a 5 dimensional group here, then only we can solve, otherwise we cannot solve this one. So minimum we have to get a 5 dimensional group here. So before starts, then we have to choose the what is the core variable here. There is a core here. So we have so many variables are there. It starts with the heat transfer coefficient, length, temperature, viscosity, density, then thermal conductivity. So like that we have the variables are there. From according to this 9 variable, we have to see what is the core variable here. The core variables are here L, mu, K, G. L length, mu is the viscosity, K, G. So we cannot use again same way. Already we chosen viscosity, there is no point choosing for again density. Same way for thermal conductivity already is there, then there is no point of heat transfer coefficient, H is no need, okay. If it's similar properties, you can always replace, but we have to choose the proper core variable. Otherwise, if we choose some other this one, then we will get a different dimensionless number here. So basically, the choosing the variable, the core variable is very, very important here, and you have to choose exactly what are the problem based on the problem. Otherwise, if you choose other things, then we will get other fundamental dimensional groups, then it will lead as a negative results. So after this one, we discussed already. So totally 5 dimensionless group. It starts with the P1, P2, then P3, P4, P5. So what is here basic fundamental dimensional group here? Fundamental dimensional here we discuss L, mu, K, G. This is a core variable. We call it as a core variable. But so we have another 9 variables are there. Then you choose another one is a rho. Rho is the 5th one. Then the Cp specific heat capacity, the 6th one. The beta volume expansion coefficient 7th one. So delta T is the 8th one. Heat transfer coefficient. This is a normally we use for convection part. The H is 9 variable. But these are fundamental core variable. Okay, main core variable here. So on this one, then we can always write La, mu B, Kc, Gd and rho. The first one is for first dimensional group. The P1 we can write always like this way. So here the P1 stands here. That's okay. This is a P1. P1 here. The P1 here. Basically, we have totally chosen the 4 fundamental dimensions here. That's a M, L, T equal to. Then you have to write for already we discussed L, mu. Go back, write the okay Kg rho, okay, Kg rho. This stands first stands length of length this one, then this is a viscosity. Viscosity we can write M by LT. Then other one is for thermal conductivity. Thermal conductivity you can write K. K is the ML T3T. Then this is the gravitational. Gravitational we can write L by T square. So but this again correspond to A, then B, then the C, then D. So now you have to take only the coefficient of L, what is L here, the same L here, and the same way for T, and then another is a temperature. So we will get a 4 this one, then we have to solve it. First you got to get a is here, A is a L stands here A. So like that you already we discussed same way here, L minus A minus B, like that to form the equation. You have to form the equation. From the equation, then we have to solve the value or get the value of what is value C stands. So here what is the meaning? C is a 0, that's the meaning. The C is 0 meaning thermal conductivity 0, the first dimensional group here. Then the B is a -1, the B is a -1, -1 is a mu. Whenever B -1, then always coming here. Then the C 0, then D 1 by 2, D 1 by 2 is the G 1 by 2, that's the value. So A is the length here, A 3 by 2, here A 3 by 2 is there, A 3 by 2. So this first one is solved here. First dimensional group P1, the first dimensional group P1. Same way we have to go and take the next equation, again expand it M, L, T, this one, then you have to solve it. When you solve here, then we will get a second group, this is called a second one, is called a Prandtl numbers. Prandtl numbers here Cp mu by K. These are dimensional numbers. We will discuss more how what are the significance of this one for forthcoming classes. So P2 is that second dimensional group, then P3 is the same way we have to use the third one, then fourth one, like that you have to take then is solve it, then we get a fourth one. The fifth one is a Nusselt number. Nusselt number we called as is a Nu is a Nusselt number. So these are because we already discussed only dimensional numbers. Here is a Nusselt number here. The Nusselt number HL by K. The H stands for heat transfer coefficient, A is the thermal conductivity, then L. So we have two already known numbers, one is the Prandtl numbers and other one is the Nusselt numbers here. So then what happened here, you take a value of the P1 because there is no number here, it's a significance here, P1, P3, P4, you multiply all three dimensional here, then we will get another number, that's called a Kirchhoff number. This only will use for always in the natural convection. There is a natural convection part, we always use this Kirchhoff number. So it's called a Kirchhoff number. Nusselt number equal to function of Kirchhoff number, then Prandtl numbers. So these are basic fundamental dimension how we derive this one, but I always use the Buckingham theorems. Okay. So now dimensional numbers, why you want to use dimensional numbers here? Because they mainly influence our main factors such as the density, the bioprocess system mainly influence the density, then viscosity, then temperature, impeller speed, thermal conductivity. These are all the mainly influence here. Then other one is for here, the dimension numbers definitely involve the many complex processes. So example, reactor configuration, sometimes liquid properties, operating condition, everywhere the dimensional groups involved, very important here. So the dimension numbers, they reduce why you want to use the dimension numbers here, very important here. It's reduce the complexity. Sometimes very difficult to solve, and if you got more than 10 or more variable, and when you use the dimensionless, it's very easy to solve that one. So you want to scale up the process. Say example, you want to scale the Reynolds number or power number with larger capacity, definitely we need thorough knowledge of the dimensionless number here. You want to improve the efficiency of experimental work, of course we need that also, then to predict the transport behavior also. So what is Reynolds number? We will discuss now what are the different type of dimensional numbers, where we want to use, everything we will discuss here. So Reynolds number here, the ratio of inertial force that is a creating motion, then viscous force the reducing motion. So inertial force the creating motion, there is a velocity is more, so that's the inertial force, then viscous force, wherever viscous force is reducing the force, the ratio of these two. So inertial force by viscous force, this is always Reynolds number. So we always write the dV rho by mu, dV rho by mu. So the V called as the inertial force, the V called always inertial force, that's a creating motion, but whenever the viscous force, the reducing motion. The ratio of these two we called as the Reynolds number. The rho stands liquid density, kg per meter cube, then use the velocity, meter per second, d is the diameter of pipe, m, then liquid viscosity is the Pascal seconds. So totally 4 variables involved in a Reynolds number. So Reynolds number, the normal thing, what is Reynolds number in the tank, what we have to do here, dV rho by mu, what we can do, V replace N D. Okay. So, here the d is again d already di, then n di, then rho by mu. So, we can write here rho n di square by mu. This is a Reynolds number for in a tank. So, here the liquid density rho is the liquid density kg per meter cube. The n is here rotational speed of the impeller. How the impeller is rotating, the speed of the impeller in terms of per rotation per second. So, then di is the diameter of the impeller, the diameter of the impeller di, the liquid viscosity is the Pascal seconds. So, if you use this one all units, it is a very simple. The density you can use kg per meter cube, of course, the velocity meter per second. Then how they are getting dimension number, just I want to show you that d is the meter diameter. By the viscosity here you can write kg per meter second. So, you all get cancelled, then we will get as a finally 1. So, what I want to say here, the Reynolds number is the dimensionless number, there is no dimension here. Same way here, if I want to write in terms of tanks, so the Reynolds number equal to rho of n di square mu, the rho unit density kg per meter cube, n is the rotation, how many the number of rotation RPS here, rotation per second. So, second inverse, the d is the diameter of impeller, that is a meter square. Viscosity, once get everything cancel, then we will get a 1, that is the dimensional numbers. Whatever number always it gives a dimensionless, there is no dimension. So, the significance of the Reynolds number, what we discuss here, then now what are the three different type of flow? One stands a laminar flow. The laminar flow, if Reynolds number is less than 2100, so we always call it Reynolds laminar flow. If the flow is pattern is very smooth and mixing is very small and negligible amount also here. The transition flow, that stands between 2100 to 4000. So, 2100 to 4000, that this range between this one we always call as a transitional flow. Whenever if Reynolds number is above 4000, so we called as a turbulent flow, that called turbulent flow. Here the excellent mixing be here and higher movement of transfer here, the velocity high here. But the transitional flow, unstable flow, but again its behavior is a mixing with the laminar and turbulent both in between flow, that is what we call as a transitional flow. So, next is the power number, sometime we write as a Newton number. So, n power number equal to P by rho n di power 5. Thus, we will discuss what are the dimensional numbers, where we will use, because whenever bioreactor if you want to use, there is a power number is the most significant here. So, the NP is the impeller power number, you always write impeller power number. The P is the how much power consumed, you have how much power consumed, that is called watts. So, how much power consumed this one. Then the rho is the liquid density kg per meter cube in terms of this one. Then n stands here the rotational speed of impeller. What is the rotational speed of this one, RPS? Then the dA is the impeller diameter, dA is the impeller diameter. So, same way here, if you use all the units, we have to get only one because of dimensional numbers, but it is not meaning that all numbers are okay dimensionless numbers, sometimes dimension number also there. But anyway, here we are not going to discuss as a biotechnology, some students it is not necessary to discuss, just we will discuss only the basics, what is the dimensional numbers here. So, the power number, the P here, the P we always write kg per meter square power, then the density kg per meter cube, then n is the speed, okay, second inverse, then diameter is a meter per 5, this is a second minus 1 cubic. So, once you get cancel everything, then we get a 1, the power number is the dimensionless variable here. So, next what is the Prandtl numbers? The Prandtl numbers define the ratio of momentum diffusivity to thermal diffusivity. So, what is the momentum diffusivity? We always write momentum diffusivity mu by rho. So, it is like kinematic viscosity. So, it is a momentum diffusivity here, then thermal diffusivity here, thermal diffusivity mu by rho, thermal diffusivity k by rho Cp. Okay. So, momentum diffusivity here, thermal diffusivity. What we discussed same thing here, mu by rho, K by rho Cp. This should look like ratio of convective heat transfer to conductive heat transfers. So, what is the movement and diffusivity? Movement and diffusivity, the absolute viscosity by density. The absolute viscosity by density we called as the movement and diffusivity. It explains the movements of the momentum due to viscosity. The ratio of dynamic viscosity to density, this one, mu by rho, we called as a movement and diffusivity. Sometimes we call it as a kinematic viscosity. The thermal diffusivity, what we are discussing, alpha equal to K by rho Cp. It's a behavior of the heat transfer. Definitely we will use the heat transfer only, the thermal diffusivity. So, the ratio of thermal conductivity to product of rho into density into specific heat capacity, that we called as a thermal diffusivity. So, the Prandtl number what we discussed here, mu by rho, then K by rho Cp, mu by rho, then K by rho Cp, then once this one, then the rho will get cancelled. So, finally, it will come as a mu Cp by K. Cp mu by K, we always write a Cp mu by K is always we write as a Prandtl numbers. We will always use the full property of that one. So, again here what is thermal viscosity, because alpha we write a thermal, the mu is a thermal viscosity, then the alpha is a thermal diffusivity. So, here rho is the density of fluid, then Cp the specific heat capacity, mu is the viscosity. If you solve it all units here, the viscosity units of course you know already we discussed here, then the specific heat also units are there, joule per kg Kelvin, then you convert again joule to in terms of kg meter per second, this one. So, finally, we get the value of here. Same way for watt per meters Kelvin, watt per meters Kelvin we can write joule second, joule per second, then meter here, finally, we get this one. Substitute all, then finally, we get the 1, that is a dimensionless numbers. So, Prandtl numbers also fall in the dimensionless numbers. So, what are the significance here? Because the Prandtl numbers here Cp mu by K, that is the Prandtl numbers. So, what happened here, if Prandtl number is less than 1, so this is the Prandtl numbers, the Prandtl number is if less than 1, so the thermal diffusivity this will dominate, because here two type of diffusivity, one is the momentum diffusivity by thermal diffusivity. If it less than 1, so this guy momentum diffusivity less than thermal diffusivity dominate, that is the meaning called less than 1. So, if it greater than 1, if it same way is greater than 1, then the momentum diffusivity dominates, that is a momentum boundary layer thickness is more than the heat transfer taken by the convection. If it both are same, if both are same meaning momentum diffusivity equal to thermal diffusivity, both are same, then the Prandtl number also NPR also 1. It is only we will use for this one, the conductive convective heat transfer taking place. Next is Smith number. So, this is similar to Prandtl numbers. Smith number is the momentum ratio of the momentum diffusivity by molecular diffusivity. Momentum diffusivity we always discuss the fluid boundary layer, then molecular diffusivity is the mass transfer boundary layer. So, the mu by rho, this is a mu by rho, then the d is the diffusivity. This is different diffusivity, not ordinary d, it is a diffusivity. This unit itself meter square per second. We always write the fixed first law, no? I hope you remember J equal to minus of d dou c by dou x. The d stands here the diffusivity, the d stands here diffusivity, that is a meter square per second, and here mu by rho there is also meter square per second. So, once you get everything, then it is like a 1, so dimension numbers, dimensionless numbers. So, we always write kinematic viscosity, then the d is the mass diffusivity, the ratio of kinematic viscosity by mass diffusivity we called as the Smith numbers. So, again NSC equal to mu by rho by d, this is a d diffusivity, the units here diffusivity meter square per second what we discussed, then this is a viscosity units here, the other one is for density. When you solve it, then finally we get a 1, is a dimensionless numbers, This is a way to do here. So, if it is 1, again here the ratio between 1 is the momentum diffusivity by mass and the diffusivity. So, here if both are same, then momentum mass both are comparable, NSE. If NSE greater than 1, then definitely the momentum, the ratio of momentum by mass diffusivity DAB. So, the momentum is very high if it is greater than 1. If it is less than 1, that the mass less than 1, that mass diffusion, this one is less, the mass diffusivity dA is the higher. So, that is why mass diffusion is the faster here. So, what are the key takeaway here? We discussed first what is the dimensional analysis here. That simplify the complex transport formula problems by combining multiple variables into a small set of dimensional group. The Buckingham theorem we discussed. Then Reynolds number, what is Reynolds number? What is the ratio of this one? Inertial force by viscous force. Next one is for power number. The power number relates the impeller geometry here. Then power number, then Prandtl numbers NPR equal to Cp mu by K. Then Smith number is the compare the moment and diffusivity to with the mass diffusivity. So, we discussed here dimensionless numbers all form of basics for the reactor design. When you want to heat exchanger analysis, then OT oxygen transfer calculation, you want to scale up the bioprocess. So, definitely we need thorough knowledge about the dimensional numbers, otherwise we cannot solve in the bioprocess problem. Thank you.